there. Basically, we looked at ballistic transport in what was called a point contact. And we realized it was not really a point contact, right, by our standards today, but it was still small enough to satisfy that relation of length scales. That L and W, the length and width of the sample, is much less than the mean free path. So that puts it in the regime of ballistic transport. And what happens in that regime is various density of state factors cancel out when you look at the transport, and all you get is a quantized conductance E square over H times the number of modes that you can couple into. These are the discrete quantized modes in the channel. And why are they discrete? Because the width is on the order of the Fermi wavelength. And then if you have some scattering within the channel, then you will get a transmission factor. So that's the T. But in the extreme limit where you had a perfect conduction through the channel, transmission is 1, and then you basically pick up the conductance of the contact. So I've written that at the end, that when T is 1, G is just equal to G contact, and that's 2E squared over H per mode. Any questions?
I'm still kind of bugged by the terminology here.
Okay.
Because that's a number, and it doesn't matter whether you use copper or iron or aluminum
Yes.
as your contact.
Yes.
So to call it the contact conductance, to me it's completely a property of the fact that your channel is experiencing quantum.
It's right. So if you were, it's important to remember, if you were tunneling into the channel, like we were doing earlier, we had a quantum dot and we were tunneling into it, then you would be determined, then the probability of conduction would be determined by the tunneling probability across the junction. But now you're just transporting. And in this case, you're right, the property of the contact, so to say, the gold or whatever lead you had, is completely gone. It's just a resistance coming from fitting certain number of carriers into a narrower constriction. So I guess what is being conveyed by the word contact is that it is coming from that constriction. It's maybe, contact seems to signify that it should depend on the property of the contact. But it's not dependent on the material property, but the constriction property.
Okay.
And yeah. So I made, I think I tried to make a better picture of, is the geometry clear to everyone? I think it is clear, right? So I think maybe the best way to think of it is, this is the length and width of the channel, and the width is being controlled by a gate voltage. Is the idea of a gate clear to everyone? What is a gate doing? Please ask if it's not. Because the actual geometry, if you want, maybe I can just show it here in terms of a 3D picture, is something like this. Here is gallium arsenide. Then there is gallium aluminum arsenide. Thin, everything is quite thin. So this is gas. And at the interface, so the 2D electron gas actually is not on the surface. It's embedded, it's buried in the interface between these two materials. It's somewhere here. So the 2D is sitting here. Is at the interface. Okay, now let me draw a 3D thing. So if I look down, the 2D gas is sitting buried, okay? And now on top of this, one is going to put a source and a drain. So here's the source and drain. So this is source and drain. And the width is something like this. Like how they tried to make it in that picture. Okay, so what you're trying to do is to put some metal pads on top, and the metal pads control the potentials. Basically, you can move charge around using metal pads, and it controls the potential, and you can essentially deplete the electrons from under the gate. Okay, if you put a negative voltage on the gate, you can deplete the electrons from under the gate, so most of the electrons are now in this region. So the gates are here. By changing Vg, can deplete the electrons under the gate, and that essentially generates this, that gives a width W, where okay, so that's the channel. Is that clear? Okay, so the next step was to look at to see. So we have one formula which tells us. So this is the Landauer formula, and which is basically this: 2e square over h mt. And we want to go all the way through the quasi-ballistic regime, so this is more or less ballistic. All the way to a diffusive regime, which is Ohm's law, Landauer and Ohm, and that's diffusive. So I found, after much hunting, I found a good book, which I should recommend to you, and that is Kittel, 8th edition. Okay, so I was never using that because I have some of the older Kittels, and I hadn't realized that they have really updated it. So Kittel's 8th edition has a special article by Paul McEwen on gosh, I don't know how he spells his name. I don't know. I know that's wrong.
EWEM.
Something like that. Anyway, it's the only article on nanosystems. But take a look at it. What is nice about it is a very comprehensive view. In one chapter, you know, all the key experiments are touched on. The bad thing is there are no references. It says, courtesy so-and-so. You know, like he picked up the phone, called his friend, said, send me a picture of the 1D density of states. Okay, and the picture is there. Send me a picture of quantized conductance, a very nice updated picture from what we looked at yesterday, showing also the temperature dependence is in that book. But there's no reference, so it's very hard for me to track it down now. Of course, you know, I can go look up the authors and so on, but it's a start. At least there's one article finally which gives an overview. Okay, and he also does this transport part very well. I'm actually going to do even a shorter discussion than that, but that is sufficient for us to get this proof, or this stuff. Okay, so let's see, what exactly is involved in this? So, yeah. So let's start here. M is basically of the order of W over Kf. It's a matter of how many wavelengths can I fit in that with W. So M is of order W over lambda f, or you can just write WKF over pi, which is 2W over lambda f. Okay, so if I put this in here, then what I get is G is equal to E square W G2D VFT over pi.
Which Fermi surface are we talking about?
Um,
Of the 2D electron gas?
No, I'm going to just write down. This is just a bunch of constants. So G2D. So I'm actually looking at a channel. I'm looking at, I'm trying to go from, so what I'm looking at is something like this, and this is W, that's also W, and this is L. Okay, and what I want to do is, I want to make it, in order to go in, so in the ballistic regime, I have LE is much bigger, so to go from here to here, what I have to do is to make the length bigger and bigger. That's one way to think about it, right? So I have a certain scattering length on this. So on this scale, let me put an N to this. Okay, so that's my L. And I'm going to make LE bigger than that. Now, on the ohm side, I basically want to go to a macroscopic system, right? So I'm going to go to W and L, much, much bigger than LE. So I've just expanded L, and what I'm going to say is that in the scale L now, which is much, much bigger than LE, so you can keep anything fixed. I'm going to think of it this way, that I'm keeping LE fixed, changing the size of the system, because that's what was done in going to nanosystems. You have a certain material with some known LE, and you're going to shrink the size. That was there. Now if we make it bigger, within the scale L, you will get a lot of scattering. And so, yeah?
So in the ohms region, like the channel is three-dimensional, and
yeah.
in lambda, well, it's two-dimensional electron gas. So
it's basically quasi-one-dimensional.
So I can understand the width, the W there. Why what is that cross section?
Sorry.
The cross section you draw in the elastic region. So so one is width. I understand.
No, both. So okay. Here, so just a second. Here I'm trying to get into a regime where I've drawn it like elongated, but I could have just drawn it like this. You know, all three dimensions are comparable. That's what I'm trying to say. In this regime, right? All the three dimensions are comparable, but you know, L is slightly bigger, that's why I've drawn it like this. To get to the ohm regime, I have to make W also bigger than LE.
Well, but like the resistance in Ohm's law is ohm meter, and here is just ohm. So how do you?
Oh, no, it's the same units. Here also G, right, will basically be equal to sigma. So R is rho L over A. So G is sigma A over L. A is W squared. A is W squared, let's say. No. Yeah, A is W squared. So it is ohm, it is inverse ohm meter. Same units. So let's see, G has units of ohm inverse. Just as here, E square over H, all of these are dimensionless. E square over H has units of inverse ohm. So E square over H is 25, 25 kilo ohm inverse. Okay. Now, is that clear? But was that your question? So the point is, okay, let's look at it. What you want to do is to get to a bulk system. Bulk basically means WL, everything is bigger than the microscopic length. You could, and that would be a 3D bulk. You know, people are interested in two-dimensional conductors and so on, and that just becomes a matter of now not expanding all dimensions. I'm not going into that story. That's yet another part of conductivity where you say, I don't want to look at conductivity of a bulk 3D system, but I want to look at a conductivity of a sheet. And in that case, again, what you're going to do is you're going to make L macroscopic, W macroscopic, but the other cross-section, the thickness, will be on the order of the wavelength of light, of electrons. And that's how that direction will now be quantized. So it depends on what you want to study. And that's another big field of study where you look at low dimensional transport in bulk. So what I'm emphasizing here is essentially transport at the level of a dot, ballistic, to bulk. Is it clear? Okay, now coming to this 2D thing. This was just a matter of if I plug in all of these constants here, what you get is, so that was just actually playing around with these constants. So this, what I have done, was written as 2e square over, and 2e square w. I see what you're saying. No, I think that's correct. Yeah, that's correct. So that's m, and then I have mkf over 2h bar square I square h bar kf over pi m times t. Okay, so if I put all of these, and I've just juggled some constants. And based on that, this is my 2D density of states. So if I cancel this out, then this is just my G2D. It was the constant density of states of a 2D system, and that's what I've written down. So it's not like I'm studying a 2D system, but that combination is just the 2D density of states times VF times transmission. Okay. So what we want to calculate, so this is what things boil down to. We are trying to go from something like this to this. This is our aim, is to go from there to there. Okay, so if you look at it, what you see is that there is a transmission T there. There's no transmission here, but somehow we need to connect these two equations. And so that's the next step. We need to understand basically transmission through a wire, through a channel in which you are getting multiple scattering. Okay, so I'm going to keep these formulas somewhere at the top, and now we will basically address what does transmission look like when we are scattering multiple times.
What Fermi wave vector are we talking about in the 2D gas?
We are talking about, not in the 2D gas, you know, we have this, so we are talking about, the thing is something like this. We have, basically, we are connecting with leads. So we have, so we are basically connecting with leads in the source and drain, and it's basically the Fermi wave vector of your source. Okay. And so essentially you're trying to inject electrons at a velocity Vf coming from the source. And as Eric pointed out yesterday to me, you can run this system in various ways where the source drain potential can be very different. Right, you know, like you can have a big difference, and that would actually probe even non-linear transport. If you remember earlier when we were looking at tunneling, we could look at the conduction as a function of VSD, right? So we could make it very small, and then, you know, we could make it bigger, and we could look at IV characteristics as a function of VSD. And that could take you, so what I mean is, here is mu1, this is mu2. So E times VSD is delta mu, mu1 minus mu2. And you can look at the current as a function of VSD, both positive and negative bias, right? And you will get some behavior like this, and then, you know, it may do various things. So this is all what is called non-linear. It's interesting in its own right. What we are trying to probe is the low voltage part of it. And the ratio from that is what is being defined as the conductance. Okay, so it's the linear regime. You're making it slightly different because if you don't make it different, there's no current. So you make it slightly different, just enough to probe the properties at the chemical potential. So that's the regime you're probing here. Okay, so let me put down this expression. So this is in the Landauer regime, and in the Ohm regime we want to get G would be equal to sigma A rho L over A, it's a sigma A over L. Okay, so let's look at two conductors. So now again, I don't want you to lose a picture of what we are doing. We are now going to look through, some multiple scatterings. So this is one scattering event. This is another scattering event. And each scattering event can be represented by something like this with a transmission coefficient T1 and a reflection coefficient R1. Okay, so now I'm going to put two conductors, two scattering events. And so what you have is right, and so we want to write down all possible terms from this. So you're going to get one term which will just be something like this. One process which will be T1 and then T2. That's the obvious one. But then you will get successive processes that look like this. So let's say T1. T1, this is R2, this is R1, and this is T2. So this process will be T1, T2, this process will be T1, T2, R1, R2, and I'll write one more. Okay, so basically you're putting down multiple scatterings, and this one you can show is just T1, T2, R1, R2 whole square. Okay, so finally what you have to do is to sum up this geometric series because of these successive scatterings. And what you get then is T12 is going to be T1, T2, And more than this, what you can show just by juggling these expressions is that if I look at 1 minus T12 over T12, okay, so it's just easy to just, this is the other equation I'm going to show here. Then this is 1 minus T1 over T1 plus okay, so these things add 1 minus, so 1 minus T1 is R1. You know, you can't add, you can't just multiply T1s to get the net probability, but it's this expression that ends up being additive. 1 minus T1 over T1 plus T2 over T1 minus T2 over T2 and so on. And you can just show that by juggling this expression. Okay. So this was the result with two scatterers. And now we can, I hate to erase this, it's such a nice geometric illustration of a nice series. You can just imagine that a particle rattling there and then emitting, rattling and then emitting. And that's what is going to lead to a transmission probability which is much higher than just the first term. Okay, so now with n identical scatterers, so now suppose I have n identical scatterers, then you'll basically get 1 minus Tn over Tn is just n times 1 minus T over T. Okay? Or this implies that Tn is equal to T over n 1 minus T plus T. Question? No. Okay. So now I'm almost home. What I'm going to do is that T in the conductance in the Landauer formula is really not this T. It's the T after you have scattered from n scatterers. So this is actually Tn. That's how I go from here to here. And the single T is just the property of any one scattering center, right? So that's where whatever kind of strong scatterer, weak scatterer, whatever determines the mean free path is the density of scatterers times the cross-section of scattering from a single scatterer. All of that is kind of buried here, and this is the result of multiple scatterings. So I can define now something like this, that the number of scatterers is n, which is density times L. It's a linear density. Yeah, this is a linear density. So this expression then, Tn, can be written as T over, T over little n, 1 minus T, divided by L, plus T over little n, 1 minus T. Okay. Which I can write as some length scale L0 over L plus L0. And this is some microscopic length. Microscopic or length, which is on the order of L elastic. Okay? Why did I call it L0? Because it has to have dimensions of L0, of length, right? And T is the scattering from a single impurity. So it's basically the property of some elementary scatterer. And I've gotten rid of the obvious density dependence. And so just to expose the length, because I'm trying to finally, at the back of my mind, I have this Ohm's law in mind, that I must extract a length scale. I have a transmission probability here, but here I have a length. So that is what is there at the back of. So whenever you're doing algebra, you have to keep in mind what you're going toward. And then based on that, you're juggling all your symbols. Because there are many other ways of juggling these symbols, depending on what you want. So I'm looking at those two expressions. I have a transmission probability in the Landauer formula, and I know it is not decaying exponentially with length. Somehow I must find that this transmission probability must go like 1 over L. And so that's what I'm trying to do. So I'm exposing the length by saying that there will be a density of scatterers, and that's how I will get the length out. Okay, so with this then, G comes out to be E squared G2D VF L0 over pi W over L plus L0. Right. And if I want to write it as a resistance, so G inverse is okay. I'm getting into a little bit of trouble here. So let's see, G, and some factors are not coming out right. So let's see, G inverse is then L plus L0 over what I was trying to show was, see, L0 is going to actually be, I'm almost actually done with my proof, except you know, this L0 is a much smaller length than L, because I have gotten into the regime where it is much bigger. But actually, if I write it out correctly, you can see that I get the contact resistance and the system resistance out of this, if I invert it correctly. So that's what I'm trying to do. But actually, just here we have the proof, but somehow at this punch moment, I'm not getting that. But give me 1 second, and I'll prove it. Okay, so let's try this. So suppose I have G inverse, then that is some of these factors. Let's see if I can write these factors better. So these factors are actually M E squared tau over M. So I should be able to just get sigma times W. Yeah. So I should be able to write all of these factors. These factors should just give me N squared tau over M. Okay, so that's something which I should be able to get. So show that E squared G2D, which is just MKF over, let's just write it out now, MKF over H bar square pi square VF L0 is VF times tau. So there's a VF tau over pi. Am I right? Yeah. Okay, so all of these factors should actually just give me N E squared tau over M. Okay, so what you're going to get is yeah, I think I can see that. Because you see, you'll get a KF cube, and I'm not going to do this right now, but you'll see from the three, there's a KF and there are 2 KFs here. The KF cube will give you an N, VF is H bar KF over M, and that's how you're getting one of the N's and I'm not able to see all of it, but this should be equal to this. Okay, so put a question mark and let's check it later. So this then gives me sigma W over L plus L0. And that implies that G inverse is L plus L0 over sigma W. There's some area, not a factor here. But okay, so that's L over sigma W plus L0 over sigma W. And this is nothing but Ohm's law. It should have been area, and there's a W missing. So that's another thing to check a little bit. There's some trivial area missing. And I think it probably came from some scattering not being normalized correctly. But okay, this is basically Ohm's law. And the second term here is a contact resistance, which is practically zero in the bulk limit. Okay, but it shows you that you get these two terms.
So you're talking much larger than L0?
Yeah, because now finally in the Ohm limit, all length scales are bigger than your microscopic length scale. So W is much bigger. Otherwise, you don't get diffusion in the third dimension, right? So if you want diffusion, then you have to make the length bigger than the elementary length. Any other question? So all of this hinged on something like this. This is the crucial expression that we derive. That Tn, the transmission Tn was L0 over L plus L0. Or if you want to neglect this L0, it's basically going like L0 over L. That is the crucial expression. And this T is now Tn. Okay, so let me just highlight the main points because all the rest is details. Essentially, the Landauer formula was of the form some fundamental constants, E square over H, number of channels, or number of modes, times T. This T was the transmission probability through the channel. Okay? When we were doing the contact story, we set it equal to 1. When we are doing like very quasi-ballistic, we just have to actually put in the fact that there is 1 or 2 scattering event. We have to just do the quantum mechanical calculation for that. We can't do all of this averaging. But when we want to go to the to the sort of Ohm limit, where all the lengths become much larger, we now want Tn, and that is now you have to put in these multiple scatterings, and that tells us that the multiple scattering transmission probability goes like 1 over L. Again, this L0 here is not important. So it goes like L0 over L. It's a dimensionless number, and that's what sets the scale. When you put that in, you basically get a G which goes like 1 over L. And that's the crucial result for Ohm's law. And that's this term here. Okay, so let me pause here and see if you have questions. Yeah.
During the multiple scattering arguments, we seem to ignore interference effects. Is that, for some reason, not an issue?
What would you say? I want to open, this is a very beautiful and a very important question. What would you say? First of all, does everyone understand the question? You know, I looked at the transmission probability through a barrier. And then I said it scatters back transmission probability. Whereas I should have looked at transmission amplitude, which would have a phase, then it would scatter back, it would pick up a different phase, and I should have put in these interference effects. Now, why did I not do that? Or what, yeah.
And after scattering, it lost the phase coherence.
So that's an assumption, that's his question. Are we
Okay.
making an assumption? If we are, why are we justified? So first, yeah.
Or if we say that the scattering events are randomly spaced, then the phases should add incoherent.
Right. So actually this is a very key question, because what we have done is actually the formalism to go from a fully quantum mechanical problem, which was the Landauer limit. Everything had become quantum mechanical. All lengths were on the order of the wavelengths of the electrons. It's fully quantum mechanical. And we are solving essentially Schrodinger equation at that point. And then we are trying to go to a classical limit. So actually, there is a regime where you can look at quantum corrections to this term. Okay, this is not the whole story. So let me, since you bring it up, let me say a little more about this. Okay, first of all, before delving into that, because that's a little longer story, any questions on this derivation? No? Okay. So the couple of things we want to fix, one is to check that this is NE squared tau over n, and the other thing is a little factor of W, which seems to have sort of gone away somewhere. But it's not critical, so I'm not going to waste time here. But when you write your notes or go over them, check for that.
So,
Yeah.
that transmission probability that's right at the bottom there,
Yes?
seems to like violate conservation of current, right? Like conservation of charge. You can't like have more current somewhere in your circuit than somewhere else. I forget.
So for each, the net for each scattering event, there's a one, total one,
Yeah.
and then T1 plus R1 will add up to 1.
Okay.
So you won't violate it.
Um,
Why do you think you're violating it?
well, you're not like, I don't mean that the charges are disappearing.
Yeah. But tell me, what do you have in mind?
Well, just any, maybe you can't use a simple circuit like Kirchhoff's law to say that, current in has to equal current out in this situation. But
I think some electrons are scattering back.
right.
So T plus R is still 1.
So is it really T1 or T minus R? The transposition?
So this is, let me just draw it like this. You have one coming in. What is going out is Tn, finally, globally, after all the scatterings you've put in, Tn is going in, and Rn is getting scattered back. And so Tn plus Rn is equal to 1. Now what is Tn? It is not just T1 times T2,
Right.
multiple probabilities, but it is that geometric sum that we have.
I see.
Because of the multiple scatterings inside. So Tn is made up of all these T1 events. Yeah? So, okay, so that's there. Now let's come to this question that Rick is asking about what happened to these, when we constructed the multiple events, like here, we were just talking in terms of T1, these were probabilities. And then, we were looking at something here, something there. It was all in terms of probabilities. And we kind of glossed over these phases. And the reason is that we were perfectly justified in doing this because we were trying to go from Landauer, which is fully quantum mechanical, since all our lengths are much, much less than LE, and these are of order lambda f. This is the reason for fully quantum mechanical. And then we are going to ohms, which is here, ohm, which is kind of semi-classical. And you know what that means. We defined it previously. And in this limit, this was the wave packet, lambda f. Here is the mean free path scattering between two events, which is LE. And all our dimensions are even bigger. Okay? So that's classical. So we were completely justified because we are trying to reach a classical limit. But still, you might ask, what would happen if I put in some of these phases? And it actually opens up a big field of study around here, which is called mesoscopic. So we are kind of dealing with nano today, all the time, because now we can make nano. But before people could make nano right away, they were already making dimensions smaller and smaller, not quite in the nanoscale, not quite on the order of lambda f, but enough to see the first corrections from quantum mechanics on transport. And I wasn't really planning to discuss this because it was a huge field of study around the 80s. But let me just tell you, some of the pictures that came out of that was really beautiful. So I'll just say a bit about that. So this is mesoscopic transport. And here one could see quantum corrections . Okay, so what do I mean by quantum corrections? I mean interference effects, okay, which we ignored right now. And the way it happened was the following, that, so I'll just tell you one or two results which were very interesting. So this is now in this mesol regime. Actually, let me do it over there. The idea was kind of neat, that you have a system and you're trying to look at transmission through that, right? And that's what you have done through all these multiple scatterings. But what happens in this interference thing is an electron comes in and let's say it scatters. It scatters from many impurities. Let's say there are some, I'm going to make a loop. So the electron scatters like this, like this, like this, and so on. Now it will make many such loops. Okay, these are just, so in trying to get out of the system, the electron is scattering around different paths. Now most of those are just random scatterings. They don't add up to much. But if the electron, so in other words, what I'm saying is, it could just get deviated like this and then go on. These are some scatterings. So this is just some random scattering pattern, random set of scattering centers. So the electron came in like this, it got scattered. Okay, and there are so many such paths, they don't matter much. But there are a set of special paths where the electron might kind of make a loop. So the electron comes, it makes a loop and then goes. Okay, I'm going to just show the loop like this. So that just means there are a bunch of impurities and it takes it along a path and then it comes like this. But now, because of quantum interference, the phases that, so each time it scatters, it picks up some phase, some random phase, which is not random, it's a property of that impurity, but it's some number, right? Then it scatters again, it picks up another number, 13 degrees, 11 degrees. So all these phases are some random things. Now when you go along a path, you will add up the net phase that you add up, e to the I k dot r. This is what I mean by the phase, which is, I'm going to define as e to the I theta. Okay? So for an event like this, what you will get is the net phase is going to be sum over theta i's for each event, here, here, etc. So this is the phase after each event. Now you can see the beauty of what is about to emerge. So you're adding up, let's say, 7 different phases, 7 different angles. You pick up some net angle. When you, in quantum mechanics, you will get an interference because these scattering events could have been traversed in 2 different ways. You could have either gone clockwise or you could have gone anti-clockwise. And in both cases, you are going to pick up essentially the same net angle but in opposite directions. So e to the I theta plus e to the minus I theta. And these will destructively interfere. Okay, these 2 paths, this way and that way. And it's that process that essentially leads to a reduction in the probability of getting out. Because you're scattering, so you're spending more time in some region, but now you're going to scatter clockwise and anti-clockwise, and that adds up the probability of being there at that center. So essentially, it's adding to the probability of localization, and therefore taking away from the probability of transmission. Okay? So let me say that again. It's entirely a property of waves. You can see this effect not just with electron waves, but you could see this also with sound waves or any other classical waves. That you can get interference from waves going one way through some scattering random medium, and you're trying to push some probability through the system, but because of this localization effect, the probability of being found at the same point r equal to this particular point is enhanced because you can get this destructive interference. Okay, so that's the main result of mesoscale physics, that these interference effects lead to enhanced probability of localization. And therefore, less transmission. So what was found is that this conductivity formula, which was something like sigma of t, so let me So the sigma, which we know as sigma 0, which is n e squared tau over m, got corrected as a sigma of L, let me say L5, minus some factor, e squared over some factor here. So the main thing, you don't need to worry about some of the detailed numbers, but the main thing is the Boltzmann result, which we know and love, is corrected. So the conductivity is reduced because of this interference effect, and you get a negative sign. That's the first thing. And then you see that your conductivity depends on some length, because obviously this interference effect is depending on something which is capturing this length scale. It has to do with phase coherence, and I want to bring up that part. So L5, have you ever used this in any experiment where you talk about phase coherence length and you fit your data to extract this length scale? Maybe not? Okay, in transport? No. I think nobody is analyzing data in this regime now. So that's what I can assume. So the point is this. These experiments sharpened our understanding of elastic length from impurities versus length from phonons. We kind of lump, this is something we have not talked about much. But when we say tau, right, what do I mean by tau? Tell me, what do we mean by tau? What is tau? What is it scattering from?
The average time from one scattering to the next scattering.
Exactly. But what are the sources of these scatterings? We've lumped everything. Impurities, phonons, right? We went through this exercise last quarter where we found that tau could be, so our tau here was coming from, and we did some kind of an equation like this. 1 over tau was 1 over tau impurities plus 1 over tau phonons plus 1 over tau electron. If you have magnetic scattering, we just lumped everything. That's actually very coarse. It gets us through a lot of things, but if you start to think about it, there is a fundamental difference between how we handle different scattering centers. And I'll tell you what I mean. What I mean is, when we talk about impurities, okay, we are talking about a conserved system. We have a system, here is my system, and the system has impurities and it has electrons, so these are my impurities. And I can write down a Hamiltonian which contains the impurities. That's not usually done when I talk about phonons. I'm talking about a Hamiltonian for electrons. The phonons are some random bath. So the way the system becomes incoherent is very different between impurities, which do cause a phase shift. E to the I k dot r is a phase shift. It causes a phase shift, but it's a phase shift you can calculate, given the property of the impurity. For a phonon, it's some bath variable. It's a classical randomizing variable. Okay, so this is kind of taking us a little outside the whole thing. Yeah?
Is it just a question of elastic versus inelastic and whether the collision absorbs momentum from the elastic?
Yeah, it's a question of elastic versus inelastic. So when I write a Hamiltonian, so here, that's a good way to say it. My Hamiltonian contains the impurity. Hamiltonian is energy conserving. So impurities are elastic. They conserve energy. They don't conserve momentum. Okay, and so L, so what we have is, okay, but whereas phonons are inelastic and they don't conserve energy or momentum. But basically they don't conserve energy. Okay? So the words now being used is as an electron scatters from impurities. So this is electron scattering. So impurity scattering. It's a very subtle term I'm using, and I don't want to go down too much this route, but I want to bring it up since it has sort of come up quite naturally. Impurity scattering changes the phase which is basically defined as k dot ri because it goes from one momentum to another, some k to k prime, changes the phase, but does not cause phase randomization or incoherence. Phase randomization Does that make sense? So it's like saying, if I decide to take these waves and do the experiment again, I will get exactly the same answer because I know what each impurity is doing. It's a calculable quantity. But then, on some scale, you hit a phonon. So here's the point. I'm hitting these different impurities, and then at some point, it exchanges a phonon. That's it. When it does that, it has completely become Markovian. It has lost all memory. Okay, so this is where there's complete phase randomization when it exchanges with a phonon, because we have not kept the phonons in our Hamiltonian. If somehow I had decided to look at a phonon impurity system together, that system conserves energy, and then I would have a different dynamics. But I'm integrating out the phonons, so the phonons end up completely randomizing the phase. So that's what is called L phi. L phi is the inelastic length scale. And this is temperature dependent. This goes like T to some power, usually denoted by P over 2. And there's a reason for the 2, but never mind. Okay. The important thing is it's temperature dependent, and the length decreases as the temperature gets higher. So L elastic is temperature independent. It's coming from impurities and impurity concentration. L phi is temperature dependent. And so what we had to contend with for the first time, we were very loose about tau as coming from every possible thing. But once these interference experiments were done, for the first time we had to address the issue of what causes resistance. And it turned out these were caused really by inelastic processes. So even though, like if I write something like this, let's assume that scattering due to phonons is very weak. So 1 over tau can basically be neglected. So the tau that you put in your formula is still the elastic tau, but you would not have gotten phase randomization if there was not some amount of phonons. Okay, let me say that again. It's a very important point. If you had a system of pure elastic scatters, which is what we are kind of approaching in these ballistic systems, you don't get resistance, you don't get incoherence. And you get it only because underlying in the system there are phonons. These phonons make the phase incoherent. And without that, you don't get resistance. But then when you quantify that with a tau, you do end up finding that the actual value is dominated by the disorder. And that's the tau that goes into sigma 0 at very low temperatures. But nevertheless, the phonons are needed in the first place to generate resistance. Okay, so this was the story, and it was beautifully tested. So what it says is this is the behavior, and it's better to write it in terms of temperature because L phi is a length. And if you write it in terms of temperature, then really the 2D limit is the interesting one because it's a much stronger singularity. It's a log singularity, and what you get is, so writing L phi as T to the minus P over 2, you get something like sigma naught plus some constant log T over some T0 to the power P over 2. So let me just draw this because it's
But sigma 0 is also temperature dependent.
Sigma 0 is also temperature dependent. I'm going to go to very low temperatures. So let me draw that. Yeah, it is, but I'm going to go in a regime where, so let me just explain that. So here, let us write down sigma as a function of, let's write down rho first, because that's what we, so typical metal. And typical insulator is doing this. Okay, and from here, let me draw now sigma versus T. Typical metal would have done this. So this is sigma naught. And insulator would have done something like, this is insulator, this is metal. Okay. Now, what I'm saying is, you can look, so this is in the Boltzmann regime. Now if you look at, so this is in the meso regime, mesoscale, which means I'm going to look at the first correction. So this is what I'm addressing now. The conductivity of a metal is increasing as I go to lower temperatures. At some point it rolls over and gives you the scattering conductivity, any square tau, tau due to impurities. But this number is affected by these interference effects. And what it says is that the conductivity is now, so T over T0 is a small, T0 sets the scale, T over T is much less than T0. So this is a fraction. So this is going to give you a negative number, right? So the conductivity is less. So that means what it is doing is something like this. It has flattened and now it's starting to drop. So this is now sigma as a function of T. Here we had already reached the low temperature scale. This is about some T0. And these are all in the millikelvin or few Kelvin, let me say. Few Kelvin. You start to see the conductivity drop logarithmically in temperature. So this is a log T decrease. So the conductivity is dropping, and this is coming from because of localization effects. Okay, so this was kind of a little long answer to that question you raised, but here it is. That so what going to smaller systems has allowed us to do the following. That we have the Boltzmann regime under control, and in that you've seen this, the conductivity plateau out, determined by impurities. Then because you are now looking at systems where your system size is on the order of the inelastic length scale, right? This is all happening only because you can manipulate length scales. So now the inelastic length scales are becoming comparable to the system size, and you're getting these localization effects and the conductivity is dropping. So this was one way to approach corrections. Now, by now, people have gone all the way to the quantum regime where it has become a dot, and basically this procedure breaks down. Because what these effects were an expansion in some kind of a perturbation series. So, you can approach a problem from two different directions always. So this is coming from the bulk direction, putting in the first correction due to quantum mechanics. And that's what you get. And this whole theory was called mesoscopic theory or weak localization or what have you. But then you can do various orders. It's not very satisfactory because your correction terms are becoming large, so then you have to drop that approach, go all the way to the other extreme, start from the nanoscale. And that's the other approach we did.
Do you have an experimental reference?
Yeah, yeah, I do. Let's see. I made a plot of this. So there's a review article. So Here I can show it to you. It doesn't show much. It just shows a straight line because they know it's a log. So they have plotted log t. The vertical axis is resistance. And, so conductance is going down, resistance is going up. And so here it is. That's the resistance. That's log t. And it's a straight line. So theory and experiment worked very closely together in this field because these effects were subtle. And because, so if theory could tell that, there's a log dependence, you could plot the data the right way. Okay, so I'll give you a reference here. There's a nice review article by Lee and Ramakrishnan. In Reviews of Modern Physics. I don't have the date, I just took one page from there. So if you look up Reviews of Modern Physics, this is the only article they wrote together. So you can find this. And there are other fascinating effects by applying a magnetic field. You can play around with this quantum interference as you can imagine. Because the magnetic field, it's like this is a bomb Aronoff phase. It will add to it. And you can play a lot of games with that. Okay. Any other questions? This kind of is a lot of information about transport, but it is one of the key quantities we look at. So
why this effect can only be seen at a very low temperature? What's the MD square?
because you want to see phase coherence. So if you have high temperatures, remember there's the inelastic length scale, right? You want to be able to scatter and over some length scale and return to the origin. You want to be able to make a loop. If your inelastic length is very short, you scatter a bit and that's it, a phonon has hit you. So you don't want to hit a phonon till you have come around back to your origin.
So it's like you want to freeze the phonon.
You want to freeze the phonons.
Yeah.
Any other questions? No?
What is script L? Little L.
Elastic length. L is elastic length. So we use different things just because of, sometimes I call it L0. This is also elastic. And sometimes we call it LE, elastic, or impurity. Yeah. Any other questions? I won't start a new topic today. I was going to start condo, and there are some really nice. So condo is something I'll start on Monday, but it's a nice example where a beautiful effect was predicted in the density of states, never observed in the bulk. But because we have quantum dots, these features have been seen for the first time. So that's a really, that's at least, we are beginning, I'm always asking myself, okay, so what did nano get us? Are we seeing something we haven't predicted? And there is another example which I will tell you about in carbon nanotubes, which is conduction. We talked about 1D electron, not 1D, but kind of electrons traveling through a wire, right? We've been talking about that. That was our Landauer transport. That is not the full story. There are other effects where essentially you cannot have a 1D conductor which is made up of electrons. So it's a very profound statement that I'm making, that we can't just think of electrons in 1D carrying current. Those are not the right quasi-particles. So that's one aspect. And so there's something called Luttinger liquid. So we've been talking about Fermi liquids. Those were the fermions in higher dimensions. You have a Fermi surface, you have excitations. These are the quasi-particles. These quasi-particles carry spin and charge. When you go to one dimension, the story breaks down. And there was a lot of theoretical work which essentially showed that these objects would be different. Spin and charge would become separated. The same object would not carry spin and charge. So I'm going to tell you about this, very bizarre story as well as I can, with just not trying to go into too much of the math, because it's a different kind of, I don't want to use the word action, but okay, it's a different kind of Hamiltonian that you write down when you get one dimension. So the main motivation is that some experiments were done very recently, and these experiments have seen spin and charge separating. So that's really very interesting, because it has happened only because of carbon nanotube being available. And then the other example is a less dramatic one, but also quite dramatic, is Kondo physics in a quantum dot, which Howard is hopefully preparing for his exam. But this is the other thing that I will tell you about on Monday. So in the meantime, if you want, there is a Physics Today article. I'll send you an email, which has some. It's a short article. You can take a look at that in the meantime. Okay. See you Tuesday. Oh, Tuesday I'm traveling. So no, Tuesday I'm not traveling. I'm back on Tuesday. I'm making it by